Hello, I'm Norman Wildberger. Today we're going to look at polynomial spaces from the point of view of linear algebra. The framework that we've established so far in this series is rather powerful. We are now able to look at aspects of calculus from a linear algebra point of view. And this will give us important new insights into a familiar subject. So, let's start with a simple example. We're going to consider polynomials of degree 3. So there's the space of polynomials of degree 3 or less. And a typical polynomial is something like this. It's an expression a0 plus a1 alpha plus a2 alpha squared plus a3 alpha cubed. The coefficients a0, a1, a2, a3 are all rational numbers, and they can be 0 or non-zero, whatever they like. Now, this space of polynomials is a linear space because we can add polynomials and we can scalar multiply polynomials. And as a linear space, this is really isomorphic to what we've been talking a lot about, four-dimensional vector space of column vectors with 4 entries. And to establish the correspondence between this space of polynomials and this space of vectors, we think about this particular map or function, phi, which takes a polynomial like this one here and assigns to it the coefficients arranged in a vector. So we just read off the 4 coefficients, put them in a vector that takes us from a polynomial to a vector. And this map is an isomorphism, and I remind you that's meaning it's a bijection, which is also preserving the scalar multiplication and the addition. Okay, we're now in a position to make a very useful definition, which applies not just to polynomials, but to lots of other situations too. We'll say that a linear space, or a vector space, same thing for us, is a space, let's call it W, which has an addition and a scalar multiplication, which is isomorphic to Vn for some n. So if we have any old space whatsoever that has an addition and a scalar multiplication, and we can find an isomorphism from that space to a space of column vectors of the appropriate dimension, then we say that we've got a linear space, or a vector space. That's the situation here. We've got these polynomials. We have an identification or an isomorphism with V4, so we can say the polynomials form a linear space, or a vector space. Now this is a little bit of a distinction from many courses in the subject. When you talk about abstract vector spaces, often you start with some axiomatics. There are often 10 or 12 axioms or particular definitions that a vector space must satisfy. We're finessing all of that. So what we're doing here replaces all the talk about abstract vector spaces by just saying that a vector space or a linear space is something that's isomorphic to our basic vector spaces, the spaces of column vectors of a certain dimension. This is a really good way of proceeding because it turns out that in the abstract theory that's usually presented in textbooks, after one sets up all this machinery to talk about vector spaces, one ends up figuring out that the only vector spaces are the ones that are isomorphic to Vn. So in some sense, the theory kind of collapses and it all becomes a little bit trivial. So there's really no need to go through a big to-do about the theory of vector spaces. They're all just basically Vn, and this definition establishes that right from the start. If we have a linear space, we can transfer ideas from the usual space of vectors to this linear space. An important application of that idea is to the notion of an ordered basis of a linear space. What does it mean? An ordered basis of a linear space, say W, is an ordered list, say B, with W1, W2, all the way up to Wn. A list of elements of W with the following properties. First of all, it's a spanning set, meaning that every vector or every element of W can be written as a linear combination of these n elements. And the set is linearly independent. What does that mean? It means that if you have a combination of these particular elements which add up to 0, a linear combination, then the only way that can happen is if each of these coefficients is 0. So this equaling 0 implies all the coefficients equal 0. So I hope these two definitions are familiar to you. We've spent some time talking about them in the context of column vectors. We're now saying that we can adopt those definitions to a general linear space because the basic ingredients just involve taking linear combinations of vectors or elements, and we can do that in a general linear space. So a basis is a set of distinguished elements which is both a spanning set and linearly independent. Our basic example, if we take our ordinary familiar space of column vectors with n elements, then a basis of it consists of the vectors e1 through en, where ei is the vector with just a single one in the ith place, zeros elsewhere. Any linear space typically has lots of different bases. So for example, if we're looking at two-dimensional space of column vectors, then here's one basis. The list vector first 1, 2, and then vector 5, minus 1. Those are two vectors which are spanning, because every vector can be written as a combination of these two. And they're linearly independent because they're not multiples of each other. So that's a basis of V2. Here's another basis, call it C, consisting of the vector minus 3, 2, and 0, minus 2. And you could choose thousands of other bases. Here's a more abstract example involving a space of polynomials. The space of polynomials that we're particularly interested in today, the space of polynomials P3 of degree 3 or less. Here's a basis for that. These are all polynomials of degree 3 or less. And it's a basis because, first of all, every polynomial of degree 3 or less can be written as a linear combination of those four polynomials. And there's no combination of these four polynomials that equals the 0 vector, or the 0 polynomial in this case, unless you choose 0 times this plus 0 times this plus 0 times this plus 0 times that. That's the only way of making the 0 polynomial. So that is a basis. We're going to see today that there are also other interesting bases of this particular polynomial space, and they're quite interesting and important. Okay, once we've got the idea of a basis, we can talk about the dimension of a linear space or a vector space. The dimension is just the number of elements in a basis. So for example, the dimension of P3 is 4 because there's 4 elements in the basis. The dimension of Vn is n because there's n elements in a basis for that. Although the space P3 of polynomials of degree 3 or less is isomorphic to V4, the space of column vectors with 4 entries, the space of polynomials is actually a richer realm than the space of vectors. We can do more with polynomials than we can with vectors because the polynomials are themselves a little bit richer. A very important example. We can translate polynomials in the sense of taking the graph of a polynomial, say There's the graph y equals x squared for the polynomial alpha squared. And we can take that graph and translate it. In this case, translating it by 3 to the right. This is now a new polynomial equation corresponding to a new polynomial. What's the equation of this, by the way? So we're shifting to the right by 3. The way you get the equation of this one from the equation of the original is to take the equation of the original and replace x with x minus 3. So x minus 3 squared, or if you want to expand it out, x squared minus 6x plus 9, this is the equation of this graph. And the reason is, for example, if you want to know what this polynomial does at a particular value, you have to take that value, subtract 3, and figure out what this equation does to that number. That's what this is saying. So take x, subtract 3, figure out what this polynomial is doing, in this case just squaring it, and that's the value at x. Of course, we can translate by more than just 3. So more generally, to translate by c, replace x by x minus c. And an important observation is that this preserves the degree of the polynomial. So if the polynomial is of degree 3 or less to begin with, when we translate it, replacing x squared with x minus 3 squared, you can see that doesn't change the degree of the polynomial. It adds some lower degree terms that weren't there before, but the top degree term is still as it was before. So we're not going outside our space of polynomials of degree 3 or less when we translate one of them. So we have these two different ways of thinking about polynomials now. We can think about a polynomial as a graph in the usual calculus kind of way. But we can also think of the space of polynomials as an abstract vector space, an abstract linear space which happens to be isomorphic to V4. So in your mind, at least, you can think of this four-dimensional space, and the elements of that space, or the vectors in that space, correspond to polynomials. Each vector corresponds to a polynomial. Each polynomial corresponds to a vector. So a natural question is, well, suppose we think about this translating by 3 operation. Input a polynomial, translated by 3, you get a new polynomial. What does that look like when we think about it at the level of this linear space, this four-dimensional space of vectors? What's happening there? Well, we're getting a linear transformation. So translating by 3 corresponds to a linear transformation of our four-dimensional space. Let's have a look. Okay, we're studying translation by 3, acting on the space of polynomials of degree 3 or less. So to try to understand that, let's look specifically at actually what happens to a general polynomial under that operation. So we start with a general polynomial in P3, a polynomial of degree 3 with arbitrary coefficients a0, a1, a2, and a3. What happens when we translate it by 3? Well, we replace each of these alphas by alpha minus 3. So there's an alpha minus 3 there, an alpha minus 3 squared, and an alpha minus 3 cubed. So when we expand it out, we have to remember how to expand out a power. So we get the a0s there. This is a1 alpha minus 3 a1. Here we have a2 times this is alpha minus 3 squared. And here is alpha minus 3 cubed. I remind you that's the binomial theorem occurring here with coefficients 1, 3, 3, 1. So it's alpha cubed, and then plus 3 times alpha squared times minus 3, plus another 3 times alpha times minus 3 squared, and finally plus minus 3 all cubed. Alright, so let's look at that. We want to write that as a polynomial. So it means we want to group together all the alpha terms of the same degree. So here are all the terms that don't involve any alpha at all. Right here, this term here, the A2 times 9 and the A3 times minus 27. There it is right there. And the terms involving alpha, so there's an alpha right here, there's an alpha here, so it's minus 6A2, and there's an alpha over here, 27A3. Then there's an alpha squared terms coming from here, an A2, and minus 9A3. And last but not least, the alpha cubed term right here just has a single coefficient A3. So as I told you before, this is in fact another polynomial of degree 3 or less. There's the constant term, something times alpha squared, something times alpha cubed. That is in fact another polynomial of degree 3. And let's call it t sub 3 of p, reminding us that what we've done is we've translated the original polynomial p, this one here, by 3. And we can think of this now as a transformation that starts with p and outputs t sub 3 of p. And this is a linear transformation. Why is it a linear transformation? Because the dependence on the original coefficients, a0, a1, a2, and a3, are all linear. This is a linear expression in those four numbers. Here's another linear expression. Here's another linear expression, and another linear expression. So let's write this linear transformation in our preferred form, in a matrix form. So in our minds, we can think about this translation by 3 as a transformation of this four-dimensional space of polynomials. So here's a picture for that. Here's our four-dimensional space of polynomials with axes in the A0, A1, A2, A3 directions. Here's the same space. Our linear transformation is doing something to this space, just multiplying by that matrix. When we have a transformation like this, what are the first things that we ask ourselves? We ask, what is the image? What is the kernel? Well, in this case, we can answer those questions immediately without any calculation, because if you have any polynomial of degree 3, it is the image of another polynomial of degree 3 by translation. Namely, the polynomial that you get by translating it negatively by 3. So I have any polynomial over here. If I move it by 3 to the left, then if I apply the transformation to that one, I'll get the original one. So every polynomial is the translate of something, meaning that the image is all of P3. And what about the kernel? What polynomial gets sent to the zero polynomial, which is just the sort of flat straight line if you graph it? Well, if you translate by something and you get the zero polynomial, what you started with must be the zero polynomial. So the kernel is just the zero vector. Only the zero vector gets sent to the zero vector. This is a particularly pleasant kind of situation where only the zero vector gets sent to the zero vector and the image is everything. It's the case that T3 is an isomorphism. That's what it means. To be surjective means that the image is everything, and injective means that the kernel is 0. So this is just an isomorphism which corresponds to our intuition. We're not collapsing anything by translating a polynomial by 3. This idea of translating a polynomial is a very important one, because hidden inside it is the derivative of a function. It's a very important and interesting insight that we can get just by looking at these polynomials of degree 3 or less. To understand that, let's make things a little bit clearer, in fact, by not translating by 3, but translating by something a little bit more general. So we're going to translate by C, but we're going to translate by C in the, not to the right, but to the left. In other words, we're going to translate by minus C. So the effect is we start with a polynomial, and we are now going to replace each of the alphas with alpha plus C. It was alpha minus 3, you may recall in the previous example, because we translated to the right. Now we're translating to the left by C. So alpha gets replaced by alpha plus C. Now this very important computation, make sure that you should do this probably on your own, okay? Just expand this out and collect terms and see what you get. Okay. You're going to get this as being the coefficient without any alpha term. This is going to be the alpha coefficient. A1, A2 times 2C, because here when you expand this you get alpha times C times 2. So it'll be a 2A2 times C times alpha. And over here 3A3C squared coming from the alpha term in the binomial expansion of this. So which will be 3 alpha C squared. That's why we're getting that. Coefficients of alpha squared, there's one coming from here, A2 alpha squared, and again from here we're getting another 3 alpha squared C coming from the binomial theorem, giving us 3A3 times C times alpha squared. And there's only one alpha cubed occurring there with coefficient A3. Have a look at these 4 coefficients. These are what we get by translating the polynomial by minus C. So this first one, I've rewritten it there. We see what that is in terms of the original polynomial. It's called the original polynomial P. That's exactly the same as the polynomial, except that the alpha has been replaced by C. So this is just P of C. Now what about this one? This is rather interesting. What is this polynomial? Well, I hope students of calculus will recognize there's a very important relation between this polynomial and this polynomial. This one is the derivative of this polynomial, also evaluated at C. And this one here is the second derivative of the polynomial divided by 2, or 2 factorial. And A3 is the third derivative of the polynomial evaluated at C, divided by 3 factorial. So what we are getting here, these coefficients are just the various derivatives of the polynomial evaluated at C with a certain additional factor here, and I'm going to explain that in a second. So make sure you've done this calculation and that you agree that these are in fact the polynomials that we get. Now very possibly some of you will not have studied calculus before, or if you have studied calculus it may be a few years and you've forgotten a lot of it, or maybe you've studied calculus and you just didn't understand it. You'll be happy to know that we are now going to be able to learn some calculus without actually doing calculus. The linear algebra that we've developed is already sufficient to establish some very important facts and formulas of calculus. Here's the main definition. Okay. This is a very important definition. It's the derivative of a polynomial. So I'm working with a general polynomial, not just a degree 3 polynomial, but it's the same kind of thing. So here's a general polynomial. A0 plus A1 alpha plus A2 alpha squared all the way up to A sub n alpha to the n. I remind you this is just a formal expression. It's just something that we write down, linear combination of powers of alpha. And what is its derivative? Its derivative, which is called P prime, or sometimes D of P, is this polynomial. This is the definition of the derivative. And what do we do? Well, the A0 term drops out. The A1 alpha is replaced here with just A1. The A2 alpha squared becomes 2 times A2 alpha. The A3 alpha cubed term, which would be the next one here, gets replaced with 3A3 alpha squared. And the last one, this term here, becomes NAN alpha to the n minus 1. And the easy way to remember this is that each one of these terms, you look at it and you take the power of alpha and you multiply that power out front and you lower the power at the same time. So A2 alpha squared, the 2 would come out front and multiply, and simultaneously the 2 is replaced with a 1. So we would get 2a2 alpha to the 1. That's the term that corresponds to this one. In other words, that's just the derivative of this part of it. So we're defining a derivative here now, not in terms of a tangent, not in terms of limits. We're defining a derivative purely as a formal thing that we do with a polynomial. Input a polynomial, output another polynomial, called its derivative. And the reason why we're doing it in this exact way is because of the computation that we made on the previous slide. And here's the theorem. I'm just repeating what we already established. That if p equals a0 plus a1 alpha plus a2 alpha squared plus a3 alpha cubed, in other words, if we only have a polynomial of degree 3 or less, then here's what we established. We established that if you take p of alpha plus c, so that was the polynomial with alpha replaced by alpha plus c, in other words, the translate of the polynomial by minus c. Now what we got is a new polynomial whose coefficients were p of c, p prime of c, p double prime of c, which means the derivative of the derivative, divided by 2 factorial times alpha squared, plus p triple prime of c, which means the derivative of the derivative of the derivative, evaluated c, divided by 3 factorial times alpha cubed. So this is just restatement of the computation that we made, and it's because of this formula that we are justified in defining the derivative this way. The derivative is defined this way, and then we can write our formula in a very nice, efficient way. And I have to remind you or tell you what this n factorial notation means. So n factorial, if n is a natural number, is by definition the product of all the numbers from 1 up to including n. So 5 factorial would be 1 times 2 times 3 times 4 times 5, which is 120. So the theorem is that if this is the polynomial, then for any number c, we replace alpha with alpha plus c, we get this expression. A new polynomial whose coefficients are pretty well just the various derivatives of the original polynomial evaluated at c, suitably divided by factorials that increase in the same way as the degrees. Fabulous, isn't it? Perhaps that's a little bit disorienting. The idea that the fundamental object, or one of the fundamental objects of calculus, namely the derivative, can be established without any idea of rates of change, without any prior understanding of the real number system, without any prior discussion of tangents to curves and slopes of tangents, without any prior understanding of limits, epsilons, and deltas. In fact, this is a very destabilizing idea here. It's a very powerful idea that a lot of calculus which masquerades as analysis is really algebra in disguise. So if you're a teacher of calculus, you might say, but wait a minute, but you're not going to be able to prove a lot of the basic properties of the derivative with this approach. For example, what about the product rule for derivatives? That p, q, if you have two polynomials p and q, and you multiply them and take the derivative, you get p prime times q plus q prime times p. Can we establish that result? Well, in fact, we can do that very easily, in fact. In fact, we can even do better. We can also establish two higher order analogs of that, which go back to Leibniz. And the proof is very simple. If we have two polynomials p and q, and we want to translate their product by minus c, in other words, replace alpha with alpha plus c, so we're looking at p times q of alpha plus c. What does it mean? Well, it just means that we're multiplying p of alpha plus c times q of alpha plus c. And we've just established that this is exactly what p of alpha plus c looks like. And here's the corresponding expression for q of alpha plus c. So there's a polynomial in alpha. There's another polynomial in alpha. And we know how to multiply two polynomials in alpha. We just multiply all the terms and group together corresponding equal powers of alpha. So when we look through here, what's the constant term? The term that doesn't involve any alphas at all. Well, there'll be a p of c times a q of c, and that's the only terms that don't have alpha. And the terms that involve just power of alpha to the 1, or just alpha by itself. Well, there'll be this term times this one. So p prime of c times q of c. And the other way of getting an alpha is to take this term and multiply it by that one. So q prime of c times p of c, all of that times alpha. And then there'll be some other stuff, but let's just stop momentarily here and notice that this already proves our basic product formula for the derivative. Because here's the constant term, here's the coefficient of alpha, then there's some other stuff, but we know that the coefficient of alpha is what we're calling the derivative of the function we're starting with, which is p times q. So the derivative of p of q, evaluated at c, is going to be exactly this expression. That's what we're writing here. P prime times q plus q prime times p. And how do we get these formulas here? Well, we just carry on with this expansion. We just write out where are the powers of alpha squared that appear, and what are all the powers of alpha cubed that appear. Let's do the alpha squared terms, and I'll leave this one for you to check. All right? So where do we get alpha squareds when we multiply this polynomial by this polynomial? Well, we can get an alpha squared here. This term times the constant term here. So that'll be p prime of c times q of c divided by 2 factorial. What happened to the 2 factorial? Well, I took it out here. Okay, so that's one term. What's another way of getting an alpha squared? We could take this alpha and multiply it by this alpha. So that's p prime of c times q prime of c. But we're having a common denominator of 2 factorial. So we have to put a 2 inside here to make things work. And the other way of getting an alpha square term is to take this alpha square term right here and to multiply it by the constant term on this side. So p of c times q double prime of c all over 2 factorial, and that 2 factorial is already out. So that's the cumulative coefficient of alpha squared over 2 factorial. And we know that that's going to be the second derivative of the product p times q evaluated at c. And so if we just write it out without any c's, it's the second derivative of p of q. The second derivative of p times q equals p prime times q plus 2 p prime q prime plus p q double prime. We're doing calculus completely algebraically using linear algebra as the basis. It's a very cool idea. This very direct connection between translating a polynomial and obtaining the derivative or the derivatives as coefficients is something that students ought to appreciate more, and teachers ought to appreciate more too. It has a number of other consequences which are fundamental and familiar formulas in calculus, but they follow directly from our basic result. That's a computation that we did on a previous slide. So I repeated that here, and I've called that star. So it's the expression p of alpha plus c as linear combinations of alpha, alpha squared, alpha cubed, and 1, with the derivatives of the polynomial appearing there, and also some factorials in the denominators. Now this formula is valid for a polynomial p in our space P3 of degree 3 or less. It's not a valid formula if you go to a polynomial of higher degree. If we go to a 4-degree polynomial, then you have to modify this in a reasonably obvious way. You have to include one more term of degree 4, which is p4 of c, the fourth derivative of p evaluated at c, times alpha to the fourth over 4 factorial. And if you go up to degree n, well, then you have to keep on going to the sequence up to degree n. But let's have a look at this particular formula for p in P3 and obtains two other related important theorems. First of all, we just replace alpha with alpha minus c in this expression. Then we get p of alpha on the left-hand side, expressed now not in terms of powers of alpha, but rather in powers of alpha minus c. So we're just replacing the alpha with alpha minus c. Alpha squared with alpha minus c squared, alpha cubed with alpha minus c cubed. In calculus, this is essentially a Taylor series. Okay, it's a Taylor series for the polynomial of degree 3 or less. And for such a polynomial, the Taylor series is actually a polynomial. It doesn't carry on past that term. It's a consequence of that formula there that we established. Another consequence is in here, set c equal to 0, a very special case. Then we get p of alpha equals p of 0 plus p prime of 0 alpha plus p double prime of 0 alpha squared over 2 factorial plus p triple prime of 0 times alpha cubed over 3 factorial. This is an interesting little expression. Here's the polynomial that we started with. Here it is expressed in powers of alpha. And what it's telling us is it's interpreting for us what the coefficients of the polynomial actually mean in terms of the derivative. So the constant term is actually the polynomial evaluated at 0. That's kind of obvious. If you replace alpha with 0 here, then p of alpha equals p of 0. But the coefficient of alpha is just the derivative of p evaluated at 0. The coefficient of alpha squared is the second derivative of p evaluated at 0 divided by 2 factorial. The coefficient of alpha cubed is the third derivative of p at 0 divided by 3 factorial. So it's giving us an interpretation of the coefficients of a polynomial in terms of the derivative of that polynomial and higher derivatives, all evaluated at the point 0, which is a rather special point related to the choice alpha, alpha squared, alpha cubed. A useful consequence of thinking about polynomial spaces from a linear algebra point of view is that various bases naturally become important. And we don't just work with one basis, we often work with several different bases that give us different points of view about the space of polynomials. We've already seen one very good example of that. Two bases that have appeared in the formulas on the previous slide. One is the standard basis, which we're calling B, consisting of just the powers of alpha. 1 alpha, alpha squared, and alpha cubed. Now another basis, which we might call the factorial basis, is the powers of alpha divided by the appropriate factorial. So there's 1 divided by 0 factorial, alpha divided by 1 factorial, alpha squared divided by 2 factorial, and alpha cubed divided by 3 factorial. I haven't put the divided by 1 factorial, the divided by 0 factorial. Both 0 factorial and 1 factorial are 1. So they don't really contribute, but you can kind of think of them as being there also, making it a little bit more uniform. So let's call this basis B, that's the standard basis, and F, the factorial basis. This gives us two different ways of looking at any situation. So for example, this polynomial P, 2 minus alpha cubed plus alpha, well, it's not exactly a polynomial in the standard form right now, but we can easily take this expression and expand it out to get a polynomial in the standard form. So please make sure that you know how to expand something like this out using the binomial theorem. Now the four coefficients that appear here can easily be put together into a vector. That's a useful thing to do. And that vector, 8 minus 11, 6 minus 1, we'll call that the coefficient vector for P with respect to the basis B. That's a coefficient vector of this polynomial with respect to this standard basis. In contrast, here's the same polynomial rewritten now in terms of the factorial basis f. So now I have an alpha squared over 2 factorial here, and so I had to multiply the coefficient by 2 to compensate to make sure that it's still equal to what it was before. And here I had to multiply this by 6 because I introduced a 6 in the denominator. Now the coefficients are 8 minus 11, 12, and minus 6. And that vector is the coefficient vector of the polynomial P with respect to the basis f. Now we saw in the last slide why we might want to consider this. This is a nice vector actually whose entries are directly related to the derivatives of the polynomial. So this 12 here is exactly the second derivative of the polynomial P evaluated at 0. That's the first derivative evaluated at 0. That's the third derivative evaluated at 0. That's the polynomial itself, or the 0th derivative evaluated at 0. So when we regard the polynomial with respect to the factorial basis, then the coefficients are exactly just the derivatives of the polynomial in order, all evaluated at 0. Gives us a nice interpretation of the coefficients. And for some purposes, it's more convenient to work with this basis. For other purposes, it's more convenient to work with this basis. You can see that if you're doing a lot of differentiation, it might be more useful to work in this basis. And here is a general theorem that kind of captures what we've been looking at in those last two examples. The connection between a basis of a linear space and an isomorphism to vectors. So we'll call it the basis isomorphism correspondence. And the theorem is that if B equals V1, V2 up to Vn is a basis of a linear space W, so rather a general linear space, then the map phi from W to n-dimensional column vectors defined by phi of W equals the coordinate vector of W with respect to B, that is an isomorphism. So let me explain what we're talking about here. We have some abstract linear space. It might be a space of vectors, it might be a space of polynomials, it might be something quite different. We have a basis for that space. Let's say n vectors, or n elements of the space. Call them V1, V2, Vn in that order. And we're assuming that's a basis, so it means that they are a spanning set and linearly independent. It means that every vector W can be written as a linear combination of those elements in exactly one way. So if you have a vector W in the space, you can write out the coordinate vector for it, just all the coefficients required to write W as a linear combination of these. That's what we mean by the coordinate vector. And the theorem is that this gives us an isomorphism. It's going from an element in W to a vector of dimension n, with n elements. And it's an isomorphism. Okay, so just a sketch of the proof. Why is this a bijection? Remember, an isomorphism means that it's got to be a bijection, and it's got to have the linear properties. Okay, so a sketch of the proof. We have to convince ourselves that phi is actually a bijection, so that it's surjective and injective, and that it respects the basic linear structure in the two spaces. So why is it a bijection? Well, any element in W, say W, can be written as a linear combination of these basis vectors in exactly one way. And so going from W in the space to the vector whose coefficients are a1, a2 up to an, that's going to be a bijection. And it's pretty easy to see that if you have W and U, you have two such expressions. Then when you add W and U, you just add the two vectors over here component-wise. And similarly when you multiply W by a scalar. Okay, so it's kind of an abstract theorem, but what it does is it just clarifies in our mind that having a basis of a linear space gives us an isomorphism to our standard vector space of column vectors. And that's a good thing because we know a lot about doing linear algebra in the context of column vectors. With column vectors, we have matrices that we can use to transform, and we can study those matrices. So the idea is if we have a general linear space, first thing to do is choose a basis. Once you've chosen a basis, then you can think of the space via this isomorphism as essentially a space of vectors. And you can apply everything that we know about working with vectors and matrices to this abstract linear space. So let's have a look at the derivative. The derivative acting on the space P3. We're going to look at it first with respect to the basis B, the standard basis. Here is what the derivative as a linear transformation does to these four basis vectors. The derivative of 1 is 0. The derivative of alpha is 1. The derivative of alpha squared is 2 alpha, and the derivative of alpha cubed is 3 alpha squared. I hope those formulas are familiar from calculus. If not, remember we defined what the derivative is. This is in fact just from the definition, from our definition of what a derivative is. And I remind you, here's what it does to a linear combination, just combining these four things. So that general polynomial goes to that one. That's what the derivative is. Now, we can think in terms of vectors. We can think in terms of this basis giving us coordinate vectors for any polynomial. And this matrix here captures the matrix formulation for the derivative. It means that if you think of a polynomial as a vector now, a vector with four components, its components with respect to this basis, then taking the derivative, what does it do? It multiplies it by this matrix. And you can see that from here. This formula here is telling us that the A0 term disappears. So imagine having A0, A1, A2, A3. If you multiply this thing out, the first thing would be A1. The next entry would be 2A2. The next entry would be 3A3. And the next entry would be 0, which is indeed what the derivative does. Another way of obtaining this matrix is to think in terms of what happens to the four basis vectors. The first basis vector, its image is represented by this column, which is 0. The second basis vector gets sent to 1, which is 1 times the first basis element. The third basis vector, A alpha squared, gets sent to 2 alpha, which is 2 alpha. That's the second basis vector. And the fourth basis vector, alpha cubed, gets sent to 3 alpha squared, 3 times the third basis vector. Now let's have a look at that same linear transformation, the derivative, from the eyes or from the point of view of the factorial basis. Now we're going to think about this factorial basis, the derivative acting on those four polynomials is a little bit different. 1 is still sent to 0, alpha is still sent to 1, but now the derivative of alpha squared over 2 factorial is exactly alpha. And the derivative of alpha cubed over 3 factorial is alpha squared over 2 factorial. Make sure you check that, right? You multiply this by 3, and the 3's cancel here, and you just have 2 factorial left. So in terms of the derivative kills this it sends alpha to 1, it sends this basis vector to this one, and it sends this basis vector to this one. And so there's the matrix for it with respect to that basis. First vector is killed, the second one is sent to the first basis vector, the third one is sent to the second, and the fourth one is sent to the third. And what this is saying is that if you take any polynomial and you look at its coefficient vector with respect to the factorial basis, you multiply this matrix on the left, then what you get is the derivative of that polynomial, also expressed in the factorial basis. This matrix being slightly simpler than this matrix, you can see why working with the factorial basis is a nice thing to do. And that clarifies a lot of formulas in calculus, to realize that a lot of formulas in calculus are made simpler by going from a standard basis, powers of alpha or powers of x, to the factorial basis where you've got powers of alpha or powers of x divided by appropriate factorials. It's a very important insight into calculus, and in fact into combinatorics too. Besides the standard basis and the factorial basis, often we are interested in other bases too. The space of polynomials is a rich space with lots of interesting bases. Another way of getting a nice basis that's connected already with what we've done is to take the standard basis and to move all of those functions over by, say, 3. So here are those 4 polynomials translated by 3. So instead of having 1 alpha, alpha squared, alpha cubed, we now have 1 alpha minus 3, alpha minus 3 squared, alpha minus 3 cubed. Those 4 polynomials are also forming a basis of our polynomial space. And let's call that basis B sub 3. Here's a picture. Those are sort of the standard basis polynomials. And here are the ones in B3 just moved over by 3. So instead of having x squared, we've moved it over by 3, so there's x minus 3 squared. Instead of having x cubed like this, we have x minus 3 all cubed. And why might we be interested in these particular polynomials? Well, remember the Taylor formula that we derived as a consequence of our basic translation formula that expresses a general polynomial in terms of powers of, say, alpha minus 3. When we saw that the coefficients involved successive derivatives of the polynomial evaluated at 3 divided by factorials. What this is just an expression for a general polynomial expressed as a linear combination of the 4 polynomials in this basis. So for example, suppose we take this particular polynomial, 2 minus alpha plus 4 alpha squared plus alpha cubed. Then you might like to try as an exercise to convince yourself that when you rewrite it in this basis, you get 62 plus 50 times alpha minus 3 plus 13 alpha minus 3 squared plus alpha minus 3 cubed. So the coefficient vector has gone from 2 minus 1, 4, 1 in the standard basis to 62, 50, 13, and 1 in this new basis B sub 3. And a natural question, I think, is how do you go smoothly from just that vector of coefficients to this vector of coefficients? Is there some nice way of obtaining this translated formula? And as usual, linear algebra helps us. We've already set up everything. All we need to do is find an appropriate matrix. And here is that matrix. It's this 4 by 4 matrix with these coefficients. If we take this matrix and we multiply by the coefficient vector for that polynomial that we just had a look at in the standard basis, Then we get the coefficient vector in the new B3 basis. Now, how did I get this matrix? Well, just think about the columns here. Let's say with the third column. How do you get that third column? That third column is obtained by just applying this matrix to 0, 0, 1, 0, the third basis vector. The third basis vector is alpha squared. So what we're really asking is, how do you express alpha squared in terms of our new basis B3? How do you write alpha squared as a linear combination of 1, alpha minus 3 squared, and alpha minus 3 cubed? Well, here's how you do it. You use these coefficients, 9, 6, and 1, and that's why there is 9, 6, and 1 appearing in that column. And how did I get this thing? How did I know how to express alpha squared in terms of these? Well, I just went backwards from something that's a little bit simpler. I just worked out what alpha plus 3 squared is in terms of the standard basis vectors 1 alpha, alpha squared. Because if I know this expression, then I can go from here just by translating by 3, by replacing alpha with alpha minus 3. And this is just obtained by expanding this thing out. All right, so please check that similar argument explains how to get that fourth column, also the second column, also the first column. So make sure that you understand how to get this matrix that represents, what does it represent? It represents changing from coordinate vector in the standard basis to a coordinate vector in our new basis B sub 3. So that's pretty interesting. We've connected linear algebra with some very interesting and important formulas in calculus, and maybe even suggested that the standard approach to calculus is not quite in the right direction. Something that I'm going to have to say a lot more about in my Math Foundation series. Okay, but now it's time for some exercises. Okay, only 3 exercises today, but the first one's rather extensive. I want you to go back through this lecture, and I want you to extend the discussion from P3 to P4. I want you to write down what happens if we consider polynomials of degree 4 and less rather than polynomials of degree 3 and less. All right, make sure you understand what happens. Exercise 20.2, find the coordinate vectors for this particular polynomial with respect to the standard basis B, the factorial basis F, and this new basis B sub 3 that we talked about. And third exercise, let's consider translation by C. Okay? That is the transformation that takes a polynomial P and replaces it with P of alpha minus C. The question is, what is the matrix for this linear transformation with respect to the standard basis B and with respect to the basis B sub 3? Okay, we've just stepped into a very interesting realm now of understanding polynomial spaces and looking at different bases in polynomial spaces for different jobs. There's a lot more to be said about this story, and next time we're going to say some more about it. We're going to introduce some new bases for, again, this same space, P sub 3. So we're emphasizing polynomial spaces in this course a lot more than they are usually talked about in standard courses. I think polynomial spaces are very important, and they explain why the setup of linear algebra is powerful. Because this abstract geometric understanding that we have applies naturally to spaces of polynomials. And also because once you've understood spaces of polynomials, you're a long ways towards understanding what calculus is all about. So it's a very important area. All right, so next time, more on bases of polynomial spaces. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.